So it's my pleasure to welcome Joost-Pieter. Joost-Pieter is a distinguished professor at Aachen University in Germany. He's very well known for his contributions to model checking, concurrency theory, probabilistic semantics. He's written a very nice book on model checking that many of you know, hopefully. I see some people are nodding. So today he'll tell us about some of his latest work on probabilistic programming. So I'm looking forward to the talk. So,
yeah. Okay. Thanks, Martin, for the introduction. So I would like to talk about predictable probabilistic programming. And I'm going to present you a technique to do deductive verification. And the main issue is that we would like to prove certain properties of probabilistic programming by reasoning at the source code level. That's basically the main idea. So let me first start, where are these programs coming from? And I start with a great paper, to my opinion, in Nature by Zubin Garamani from the Cambridge ML group. And his slogan is, there are several reasons why probabilistic programming could prove to be revolutionary for machine intelligence and scientific modeling. Anybody who's interested in probabilistic programming, I would strongly encourage to read this paper. I get back to this in later on. So what are probabilistic programs? They're basically programs that have two ingredients. They're random assignments and conditioning. So random assignments are very neat to describe randomized algorithms. And conditioning is used to describe stochastic decision making, like you have in probabilistic graphical models. I guess you all know how you can sort by flipping coins, but let's just repeat. Here you have Quicksort, right? I mean, everybody knows Quicksort, so there is no reason to explain this, except that you pick at some point a pivot element, and based on that pivot element, you split the array in two or three parts. What you can also do, and this has the worst case complexity of n squared, right? Now, you can also do this by randomized, so the only difference between the program on the left and the right is that here we choose the pivot by flipping a coin which is has a number of possibility outcomes which is similar to is equal to the cardinality of the input array. So you just take a uniform distribution between 1 and the size of the array, and then based on that randomly picked element, you split the array in two. And then actually it turns out that the worst case complexity is n log n, expected number of comparisons. So basically, this randomization is used to reduce the probability of having those cases that give rise to the worst case complexity, right? Good. These algorithms are called Sherwood algorithms, and Robin Hood was living in the Sherwood algorithms. That's why this picture is there. Another important area is these probabilistic graphical models that I mentioned. There are seminal books on these probabilistic graphical models, and one of the main models that people look at are Bayesian networks. These are acyclic directed graphs. Vertices are random variables, and the edges say something about the causal dependencies between those random variables. So this is a very simple model for a student's mood after an exam. This person may be not prepared or may be prepared with a certain probability. The difficulty of the exam may be low or high with a certain probability. And then what you see, the grade is then depending on the difficulty and the preparation level of the student. You either get a low grade, which means you fail or you pass. Right? And based on this, you have a mood, and then basically based on your grade, your mood is good or bad, right? And they're random, these probabilities are all around. And then typical questions that people in Bayesian inference ask, how likely does a well-prepared student, so you know the preparation is good, end up with a bad mood? Yeah? These are the kind of inference questions that people are answering. And exact inference on these networks is NP complete. So people most of the time use approximate reasoning. Now, this was a very simple example just to impress you by a more larger example. Those Bayesian networks are used in many different application areas. This is an arbitrary picture that I took from a paper on ecology. And here the question was about irrigation rights or pumping restrictions on some kind of pumping thing in Spain. The question here basically is those pictures become very, very complicated. They're not easy to understand anymore. And that has been the main reason for people to look at probabilistic programming. So Dan Roy at MIT in his dissertation says the following: the graphical modeling formalism that ushered in an era of rapid progress in AI, Bayesian networks, Markov random fields, etc., they have proven inadequate in the face of these new challenges, more complex systems. So he says a promising new approach that tries to bridge this gap is probabilistic programming. And what is probabilistic programming? It marries probability theory, statistics, and programming languages. So that's what I'm going to talk about. Okay, so there are many applications of probabilistic programming. I mentioned already randomized algorithms and things like Bayesian networks, but also people in robotics use this. Actually, there's a whole group in Stanford working on cognitive science. They work with probabilistic programs. Actually, they develop probabilistic programs. People in quantum computing, they have quantum programs. If you look carefully at their semantics, it's basically a probabilistic program. And an application area which is also fascinating is approximate computing. And this is not a bug, this is a feature. Sometimes you would like to lower the energy by basically allowing that sometimes you get a wrong answer. Yeah? And people use probabilistic programs to describe and reason about these kind of systems. Okay, now there are many languages. Basically, for every programming language you know, there is a probabilistic version. Of course, there is a probabilistic version of C, there is a probabilistic version of Prolog, there's a probabilistic version of JavaScript, there's a probabilistic version of Scala, Python, Excel, so Excel tables like you have in Microsoft applications. And the famous statistical language R has also a kind of probabilistic programming flavor developed by Microsoft, R2. What is the interesting thing? These languages are not developed typically by programming language experts. They are developed by people from different areas. For instance, Noah Goodman, he's a professor at Stanford in cognitive science, and he uses probabilistic programs. And actually, there are several groups in Microsoft. Actually, Tabular and R2 are two examples of languages developed at Microsoft. Good. So I would like to start with explaining you a kind of, I would say, assembler language of probabilistic programming. For the sake of this talk, I will stick to discrete random variables. So I will not talk about Gaussian distribution and so on, just discrete probabilities. And the way I'm going to do this is by introducing the probabilistic guarded command language. So what is the probabilistic guarded command language? Well, this it's just a sequential programming language where you have statements that you cannot do anything. This means you abort your program. You have assignments, you have sequential compositions, if, then, else, and while loops, like everybody knows. And there are two new ingredients, if you want. There is a probabilistic choice. This means proc1 is executed with probability p, proc2 with probability 1 minus p. P can be a value, but P can also be an expression in terms of your program variables, and it can even be an unknown. And observe means a kind of conditioning, and I'm going to explain this by a couple of examples. Okay? Good. So let's start simple. This is a very simple program. You do two random assignments, one to x and one to y. Both you flip a fair coin. And this program, of course, admits 4 runs, and all runs have the equal probability of a quarter. I think this should not be so much of a surprise. So let's look at the Loopy program. So let P be an arbitrary probability strictly between 0 and 1. What we're going to do is we just have a Boolean that controls basically the termination of the loop, and you have a counter I. As long as C holds, you increase the counter, you flip this coin. With probability P, you set this to false, which means the program is going to terminate. With 1 minus P, the program takes another iteration. Okay? What's the distribution that this program describes? It's also not so difficult. It's a geometric distribution with probability P. Yeah? So because at the end of on termination of this program, the probability that the program variable I equals n is 1 minus P to the power n minus 1, because you have done this alternative n minus 1 times, which happens with 1 minus P. And finally, you take the left alternative, which happens with probability P. Good. Looks all pretty easy. So one remark about termination. This program does not always terminate, because there is one behavior, namely where you flip the coin and you always take the right alternative. This is a possible behavior. It happens, however, with probability 0. Yeah? So this program does not always terminate, but it almost surely terminates. It terminates with probability 1. That's what it means. Okay, now let's look at this conditioning feature that I mentioned before, that people use, in particular in Bayesian networks. So same program as before, and now I insert this observe statement that says at the end of the day, the sum of x and y must equal 0. What this is going to mean is that every run of the program that violates this guard is basically ignored. If there would be something below, you would not execute it. Okay? But in addition, you're going to normalize the probabilities. So this program has 2 runs, because there are only 2 runs that satisfy x plus y equals 0, namely 0, 0, and 1 minus 1. They have the equal probability of 1/4. But now the crucial point, you normalize over the probability of the behaviors that do not satisfy this thing. And then you get a half.
That's, I guess, if we replace observe with if x plus y equals 0, then skip also.
Not exactly. Yeah, exactly. The normalization is the key issue. Yeah? That's also the difference with an assert statement. Yeah? Okay. So observations, these kind of observed statements, normalize the probability of the feasible runs. The feasible runs are the ones satisfying your observed statement guides. Good, let's look at the Loopy program. Same program as before. Remember, geometric distribution, and now we make an observed statement at the end. By the way, you can put those observed statements, of course, everywhere. My examples only put them at the end. And now you see I is an odd number. Okay, so what does that mean? Well, first we have to compute the probability of a feasible run. Well, that's just a geometric series over all possibilities of having an odd number, right? 2n plus 1. Look at the exponents, which means you get an odd number of things, and that's 1 over 2 minus p. So with that probability, your program is feasible. So what's the distribution that this program describes? It's a geometric distribution normalized by this factor over here. And normalized here means you multiply it with this 2 minus p, the denominator. Yeah? So of course, the probability of having an even number is 0. The probability of an odd number as being this geometric distribution times this probability that your run is feasible. Okay, so far so good. Now I would like to be able to reason about these programs. And the way we're going to do that is by means of predicate transformations. So by using weakest preconditions. So let's look how people typically look at probabilistic programs, things like Bayesian networks. People use simulation techniques, rejection sampling, techniques like MCMC. These are favorable techniques to do approximate Bayesian reasoning. Good. Well, it turns out that lifting those simulation techniques to the more powerful and more expressive probabilistic programs is difficult. Actually, there was a nice paper in 2015 that showed that adopting this famous algorithm to some kind of arbitrary probabilistic program is actually erroneous. So you have to do something about this. This is not so easy. Then simulative analysis, of course, comes with weak guarantees. You get with a certain confidence, you get certain results. I like to have hard confidence. And finally, the analyses are not always guaranteed to terminate. Yeah? Because you simulate your program, how do you know upfront that your program is going to terminate or almost surely going to terminate? I'm going back to this issue that this turns out to be much harder than ordinary termination. So it's an assumption that is very strong that you make here. So verifiable programs are preferable to simulative guarantees. That's basically my slogan. So I go back to you to the non-probabilistic case, and I go back to you to the 70s, Dijkstra. I guess everybody knows what's a predicate. You take a program state, map it to a Boolean. Okay, easy. What's a predicate transformer? It takes a predicate, maps it to a predicate. Good. What is a weakest precondition? It's a predicate transformer. It takes as input a program and a postcondition, and it gives you a precondition. Which precondition? Well, the weakest precondition, such that if you start your program there, the program will terminate and finalize, actually in this terminal state, establish the postcondition. So in the sense of Hoare triples, it means that you can annotate the program in such a thing, and this holds for total correctness if the precondition implies the weakest precondition. Yeah? Good, easy. What's the weakest liberal precondition? Well, colloquially stated, it's the WP, or you allow the program to diverge. Yeah? That's the partial correctness. Good, so far, easy. So you can, how Dijkstra defined this is just by structural induction on his programs. And as you see, I kicked out, of course, all the probabilistic aspects because this is a non-probabilistic setting. And he does this by induction. I'm not going through all the cases, but it's clear that the weakest precondition of a program P, if you want to establish the postcondition F, if the program doesn't do anything, it's just F. If it aborts, it's false. Yeah, because you will never establish basically the postcondition. If you do sequential composition, it's function composition. If you do if then else, you take the guard. If the guard holds, you take the first alternative. Otherwise, if the guard doesn't hold, you take the second alternative. The most crucial and difficult part is the loop. And the loop is defined in terms of a least fixed point. And the least fixed point basically says, as long as the guard holds, you're going to execute the body. If the guard doesn't hold, then the loop terminates and you have to establish the post condition. Yeah. Good. I guess this is common knowledge, and it's just here as a kind of aha alertness for you. So the WLP semantics just differs from the while and the abort. While is getting the largest fixed point, abort is getting true rather than false, because you allow the program to terminate. So how does this work in the probabilistic setting? So here I'm going to use a terminology by MacGyver and Morgan. It's not the most adequate one, but it's called an expectation. So mind this footnote, it's not an expectation in terms of an expected value of a random variable. An expectation in my talk will be a random variable, period. Good. What is this? It maps a program state until non-negative reals. So it's the quantitative analog of a predicate. Yeah? We don't get 0, 1 anymore, but we get a non-negative real. Good. Now we have an and then we have an ordering of those functions, which is just a pointwise lifting on all states. Now I have an expectation transformer, like a predicate transformer. It takes an expectation, gives you an expectation. Fine. Now I can define the weakest one. So again, in a similar vein, you can define the weakest pre-expectation of P with respect to an expectation. So I use small letters for expectations, capital letters for predicates. And this gives you the least expectation on the initial state, ensuring that P will terminate and establish F. Good. So far, so good. So that means you can annotate your programs in a similar way as Hoare did for total correctness if, well, the precondition implies the weakest precondition in the quantitative setting. It means that E is at most, pointwise, the weakest pre-expectation of P with respect to your post-expectation. Good. The same you can do with WLP. It becomes then the WP plus the program, the probability that your program diverges. Yeah? Before we had or the program diverges, now you get the probability of divergence. Okay, now in the same way as Dijkstra, you can define this by structural induction. Of course, now we also look at the observed statement and the probabilistic choice. Yeah? And this looks very similar as before. Abort now becomes the quantitative analog of false, which is 0. Observed means these are the Iverson brackets. This means this is 1 if G holds and 0 otherwise. And then you have a scalar multiplication with F. If then else is as before. And now you have a probabilistic choice. With probability P, you take the first alternative. With probability 1 minus P, you take the second alternative. So it's a weighted choice, so to speak. Fixed point, again, for the while loop. Now, of course, your domain is a bit changed, so this is the least fixed point with respect to this pointwise ordering I explained to you on the expectations. Yeah, so very similar as before. The WLP semantics differs because we only have to change this in the largest fixed point, and this becomes 1, because you diverge with probability 1. Good. Okay, now you can define the correctness of this semantics in several ways, and one way to do that is you take an operational semantics of the programs in terms of Markov chains. I'm not going to give you spell out the details there, which is basically here on the right-hand side. And I can basically take the semantics I just defined you, but remember, I have to do this normalization. This normalization was not in my definition. The normalization is here. Yeah? And the crucial point is that I normalize with respect to the WLP, because divergent behaviors also count as violating or non-violating my observations. That's the crucial point. So this basically is the normalization that we have seen on those 2 examples I showed you before. And what does that mean operationally? I take a program, I give you a Markov chain of this program. This is this one over here. And now what you do, you're interested in establishing the post condition. Where do you establish the post condition? At the terminal states. So at the terminal states, you establish the post condition. So you're interested in reaching the terminal states, but of course you should never visit states where you violate an observation. Yeah, so it's a conditional expected reward. Where the reward is established, all states have reward 0, but in the post condition, you would like to establish your post condition in all the terminal states. Okay. Good. So this gives you some kind of operational interpretation to this WP and WLP. And you can compute those if you have a finite Markov chain in polynomial time. So let's look at this example. This was this Bayesian network of the mood of a student after an exam. You can easily equip this into a program. First, it's an acyclic graph. So what I'm going to do is I'm going to take a topological sort of those vertices. Let's put them in this order, for instance. Now, every conditional probability table is literally translated in this very simple program. Yeah. So you say this is basically corresponding to this row, and then you see with 0.95 this holds, so with 0.005 that holds. That's pretty straightforward. And now you condition on the evidence. Remember my query was, what is the probability of having a bad mood if you are well prepared? Yeah, this well prepared is now my observation in some sense, and I encode my observation here immediately as a loop. So you do D, P, G, and M. So you get these kind of programs in sequence until you get your observation P equals 1. And this is a probabilistic program that corresponds to your Bayesian network. Is this correct? Yes, this is correct. What you can show is the following. The WP of this program of the Bayesian network with respect to your observations is equal to the conditional probability of the joint distribution that your Bayesian network describes. What this slide says in one line is basically exact Bayesian inference can be done by doing WP reasoning on programs. Yeah, that's basically the bottom line here. Okay, for instance, if I would like to compute the WP of my program before with respect to these conditions, then actually what you can do, you can just reason in your program. It just has one simple loop, so it's very easy actually to reason about the loop. Remember the fixed point. Now, typically you don't reason about fixed point, right? What do you do if you want to reason about loops? You need loop invariance. Yeah? But Bayesian networks are very simple because those loops are independent. Every time you do a loop iteration, your new sample is statistically independent of your previous loop iteration. And that means that in this special case, I can give you a closed form formula for the loop invariant. So I can do exact reasoning without being needed to compute a loop invariant. Yeah? What I'm saying is Bayesian networks are simple probabilistic programs. Okay, good. Now, one critical point in probabilistic programs is termination. So I would like to spend some words on termination. So this program we have seen before. This was my geometric distribution, and already was arguing this does not always terminate. It has one behavior, namely always taking the right alternative, but this behavior takes measure 0. Good. So you have certain termination. Does your program always terminate? You have termination with probability 1, and we call this almost sure termination. And we also have a notion where you almost surely terminate, but in the expected finite number of steps. Now, this sounds a bit contradictory, right? I mean, termination in the ordinary sense means, of course, you terminate after finitely many steps. Yeah? This is obvious. In probabilistic setting, this is no longer true. You can have a program that terminates with probability 1, but it takes on expectation infinitely many steps to do so. Good, let's look at some examples. This program we have seen before, it almost surely terminates, and it terminates in finite expected time. Why? Yeah, it's a geometric distribution. The expected value of a geometric distribution is finite. End of argument. Good. Well, what about this program? It's a one-dimensional symmetric random walk. So you walk on a line. You start at some arbitrary position, let's say 10. As long as you did not hit 0, what are you going to do? You flip a fair coin, and based on its outcomes, you move one position to the left or one position to the right. This program is almost surely terminating. With probability 1, you will hit 0. You can go arbitrarily to the right, but at some point you will turn back and get to 0. What's the expected number of steps to do that? It's infinite. Yeah? So this program is an example of negative, almost sure termination. Now, there are even more weird things going on. Suppose I give you the program on the left. This program is, as before, you flip now a fair coin, and that determines the termination of the loop. And rather, by incrementing a counter in every iteration, I double a counter. That's the only difference. Yeah? Good. So This almost surely terminates and does so in finite expected time, expected value of a geometric distribution. I give you a second program that is just not even probabilistic. It just counts down. It certainly terminates, so it has a finite expected termination time. And now I run the first program and then the second program. Then what I get is I get a program that almost surely terminates but needs infinite expected time. So what does that mean? Positive almost sure termination, that's the terminology of almost sure termination in finite expected time, is not compositional with respect to sequential composition. Yeah. Why is this? Well, the termination probability of this program is decaying exponentially. And in some sense, this exponential decay is compensated by the exponential growth of x. And then you count down linearly. Yeah? That's basically the whole point. Yeah. Okay. So termination is hard. How hard? Well, almost sure termination is more undecidable than certain termination. By certain termination, I mean the halting problem for ordinary programs. One input, does your program stop or not, which is sigma 1 complete. This is pi 2 complete. So it's higher in the arithmetic hierarchy. So what you actually can prove is that almost sure termination of a probabilistic program for one input is as hard as proving whether a non-probabilistic program terminates certainly for all inputs. Yeah, that's basically the hardness gap you have to cover. And then if you're interested in this positive almost sure termination, do you in addition terminate with probability 1 and infinite expected amount of time? It's 1 degree higher, undecidable. It's pi 3 complete. So that means that these are hard problems. Yeah? So it means that if you do simulation of these things, of programs, you cannot just assume that your program is always going to terminate, because how are you going to check this? Yeah? Okay, good. So how would you prove termination of an ordinary program, a non-probabilistic program? Now, you take a variant function, right, v. You take every loop iteration on the x-axis. What does this variant function need to do? It needs to decrement in every step, and it needs to hit 0. Yeah? That's basically how you would prove the ordinary termination of a non-probabilistic program. And the important point, of course, is if I take two this is the start of the fourth loop, let's say, and this is the start of the fifth iteration, then what you would like to have is things like this. Yeah? Well, this is a well-founded order. What do we have? If arrival at 0 is guaranteed because the order is well-founded. Yeah? This is the way you prove this. Now, how does that do for probabilistic programs? This does not work. Why doesn't it work? Well, look at this random walk. It decreases, but who guarantees me that it's going to decrease? There is no guarantee. So you cannot use the standard off-the-shelf technique to prove termination of your program. Yeah? And actually, there are many proof rules for probabilistic programs in the literature, and most of them have severe problems to deal with this particular problem. Good, but what's the observation? The observation is that on every loop iteration, you decrease x by 1 with probability 1/2. Simple observation. I'm going to show you that this observation can be captured by a proof rule, and that's all we need. So I'm going to claim you can prove this, let's say, termination of almost sure termination of this program just by this observation. Okay. So we want to prove almost sure termination of a probabilistic program. So I have such a loop, and P is a probabilistic program. The way we're going to do is now we're going to take a random analog of the variant function, v, and this is now a super martingale. This sounds complicated. It's nothing else than a random variable that on expectation is going to descend. Yeah? So it's the stochastic analog of a variant function. Now, what is going to guarantee? If you execute P, this loop body, on a state satisfying the guard, then this should not increase the expected value of this random variable. So on expectation, this thing should not go, let's say, increase. For the rest, if the loop terminates, that means that v of the state S must be equal to 0, same as this variant function hitting 0. And now it comes. That's the more complicated part, but I have a picture to declare. We have a progress condition. On each loop iteration, the value of v, small v is the value of this random variable, this needs to decrease with at least this value d of v, so this d is a function, with probability at least p of v. Okay? So this p stands for probability, d stands for decrease, and the crucial point is these two functions are antitone, which is the opposite of monotone. Yeah? Good. So let's see a picture, and then if you are able to establish this, then you can prove that your program terminates almost surely on every input. So let's see how this works in a picture. Again, same picture as before, loop iterations, and now I have this super martingale, and on expectation, this is going down. So let's look at two loop iterations, those two. What does the progress condition mean? The progress condition says, look at basically at this thing, but take the function applied to that value. Okay, basically this is a kind of the way it goes down, but it doesn't go down with the difference. It goes down with this difference on this function. And this needs to be happen with probability, at least the probability, depending on this starting point on your loop. Okay, now look at another two iterations, the fourth and the fifth iteration. Same issue. They should differ with a certain difference. This difference must be established with at least this probability. And now it comes into the play the antitone properties of the two functions. Because the two antitone means that actually this value is at least that value, because d is antitone. And also p is antitone. What does that mean? It means that this probability is at least that probability. That means basically the more you go to the right, the probabilities increase, and the way you're going to decrease is going to grow. Why is that? Yeah, because I don't want a behavior that says I go with a half, a quarter, 1/8, 1/16, 1/32. I never hit 0. Yeah? That would not be sufficient to prove termination, right? Okay, so what can you prove? You get an almost sure arrival at this point 0, and this is guaranteed by the proof rule that was on the previous slide. So actually the bottom line basically means the closer to termination, the more v is going to decrease, and this becomes more likely. That's basically in one line the whole proof rule. Yeah. So how does this work? Here was the random walk. What is the witness of almost sure termination? I take the value of x, and I know that the value of x is going to decrease by 1 on expectation with probability 1/2. And that's all. End of proof. Yeah, because the proof rule is sound. Good, that's all you need. Now let's look at the symmetric in the limit random walk. This is a bit more tricky. So here you have a random walk. Again, you go with a certain probability to the left or one position to the right, but now this probability p depends on the position where you are. Yeah? In the beginning, you drift more to the right. I mean, plug in, for instance, the value 1, right? Then this is 1 divided by 3. So with probability 1/3, you go to the left, or with probability 2/3, you drift away from where you want to go. And the way you're going to drift away is going to decrease, and at some point in the limit is going to be 1/2. Yeah? How are you going to prove that this almost surely terminates? Now you can provide a witness. And the witness, I'm not saying this is an easy witness, but it turns out that v, where you take v is the harmonic number of x. So x is the position of the random walk. Harmonic number is this sum, right? This works. P of v is 1/3, and d of v is 1/k if v is larger than 0 and between the two harmonic numbers, and otherwise it's 1. And you can plug this in. This is the way it works. So here you see that with probability 2/3, you go to the left, to the right, you drift away from where you want to go. 3/5, 4/7, etc. And the limit you go to 1/2. Nonetheless, you almost surely, with probability 1, you will get back to this state. Yeah? And the way to prove this is the crucial point. I mean, these things are going to depend on x, and the decrease that you have is not constant anymore, like we had in the symmetric random walk, but depends on your position. And the proof rule is able to capture this. Good. How much time do I have left, Martin? 10 minutes. Wonderful. Good. So now we have seen how you can do something about almost sure termination. Now I would like to say something about loop invariance. Now, we know from ordinary program analysis that finding a loop invariant is not easy, so in the probabilistic setting, this will not be easier, right? So I'm going to give you one technique that you could try to apply. So, and the way I'm going to do that is by means of an example. I take a random variable x, which is a geometric distribution with parameter p, and y is a geometric distribution with probability q. I want a program that computes x minus y. How would you do that? Well, I guess you would come up with something like this. You start by having a counter stone to 0. In the first iteration, you're going to basically increment the counter. How are you going to do this? Well, with probability p, because that's what you're going to do. You take a sample of this random variable to increase the value. Then, of course, you have to reset your termination condition. And in the second iteration, you count down according to capital Y. So this is exactly with this q, you decrement x. And then at the end, I guess you all agree that if you have x, you get a sample of x minus y. Now, that's the way I would program such a thing. So this is a program, but just a bit of short notation. Now here I give you an alternative program that does the following. We start by flipping a fair coin. And based on the outcome of this fair coin, I'm going to execute the first loop only, or only the second loop. That's it. So based on this outcome, either I do the first loop with probability p, or I do the second loop with probability q, I count down. Okay, question? For which p and q are these two programs equivalent? Equivalent means expected value of x is the same, or if you want, the probability distribution function is the same. Okay? Good. Actually, it turns out that those two programs are equivalent for any q where q is 1 over 2 minus p. Yeah? So now let me show you how you could try to prove such a thing. And the way to do that is we're going to synthesize the loop invariants. And the way to do that was inspired by this CAF 2002 paper from the group of Manna, where the idea is that you speculatively annotate a while loop with some certain expressions. And notice that here I'm going to focus myself to linear programs. What are linear programs? The right-hand sides of assignments are linear. The guards of loops are linear. The guards of if-then-else things are linear expressions. So I'm basically guessing that maybe my invariant is a linear expression. x1, xn, etc. are my program variables. The alphas are the template variables. So these are additional variables that I introduce in my template. The black part is the qualitative invariant. This is the usual thing that, for instance, in this paper is used. And we added this red part, which is the quantitative thing. This says something about the expected value, the expectation of a program. Similar thing, it's a linear expression, but now with a couple of new variables, those betas. So we're going to transform these numerical constraints into Boolean predicates. You can transform these predicates into nonlinear first-order formulas, and then you can do things like quantifier elimination. And actually, we there use some black box technology, and you can try to simplify the resulting formulas. Okay? Yes? Universally quantified. Yeah. Sorry, you? Yes. And you can prove that this technique has the following property. For any linear program and that has a linear expectation, you will find all parameter solutions. Parameter solutions, I mean the parameters of the template, those alphas and betas, that make the template valid and nothing else. And this has been implemented, and the most important point is things that we use, VC conditions, like Nate mentioned already before, verification conditions. You put them into standard technology, do quantifier elimination, and then you use some kind of simplification tool to simplify this, and this gives an invariant. So this tool is called Princess. It's called the probabilistic invariant synthesis. And now how to do this for this example. These were the two programs. You can plug in a template. For instance, x plus f is 0 times alpha. And now you can put this template into the tool, and it will find for you that this means the left program, the first loop. This means the left program, the second loop. Right program, first loop. Right program, second loop. It will synthesize for you the values. And finally, you can do some analysis by saying the expected value is this, and then you can use some standard numerical techniques to solve it. And then you get the solution Q is 1 over 2 minus P. Okay, I finally like to talk about recursion a few minutes and then we stop. And the way my motivation is the following example. It's, so the question is, what's the probability that this following program is terminating? This program is a recursive program. With probability half it stops, or with probability half it invokes itself 3 times in a sequence. Okay? Question, with which probability this is going to terminate? If this would be 2, it's 1. So if you would invoke P yourself twice in a row, it's almost surely terminating, but now no longer, as we're going to see. The interesting thing about this program is it only has one probability, which is a rational number. We're going to see that the termination probability is an irrational number. Good, you can give a semantics, I'm going to skip the details. It's basically the limit of the inlining, and then you can define the WP of a recursive call with respect to a post expectation as kind of some prima of these approximations. Okay, and this corresponds to a fixed point, but now at one level higher at the environment transformation. So this is an operational view. It's a push-down Markov chain. Here I have the same program as before. I annotated it with numbers. Those numbers correspond to the control states in my push-down automaton. So let's, for instance, look at here. You start in this state. We flip a coin, and let's suppose that we flip the coin and go to this state, to this program, call P, which means in the push-down automaton we go to the left. What do we have to do? Well, of course, if we're going to invoke this, we have to recall the return address, which is the next statement, which is 4. So we push 4 onto the stack. We go to the initial state. Let's now suppose that in the recursive thing we flip the coin and now we go to skip. What does that mean? We go to the right. Then we go to this termination state. Well, 4 is on the stack, right? So we pop 4. Now we have to push 5, which is the next thing, which is happening here. Okay, the question I posed you is equal to the question, what is the probability that this push-down Markov chain will end up there? Yeah? Good. And actually, that's basically what's written down here. Let's skip the details. You can also develop proof rules. Remember my beginning, I want to prove properties at the syntax level. Yeah? Not at the automaton level, not on reasoning on the push-down automaton. I want to reason about the program, the code. These are standard proof rules for recursion, and you can also do things with lower and upper bounds. Basically, if you can say something about the call between a lower and upper bound, and from that you can take the body of the procedure and then do that for, if you're able to prove that this is basically increasing the bound by n by 1, then you can take something about the supremum, which is the whole program. So you can do this a kind of, yeah, by induction, I would say. Yeah? I'm almost done. So the termination probability turns out to be the golden ratio, yeah, of this program. And the way to see this, intuitively speaking, is the probability that this is going to terminate is 1 times a half, so it's a half, plus a half times the termination of probability of P times the termination probability of P times the termination probability of P. So you have to solve the equation. Your termination probability x equals a half plus a half times x to the power 3. And the solution of this is the golden ratio. Now, the nice thing is that you can also now do this on the code level. I'm going to skip the details, but this is how the proof looks like. And that means that by reasoning on the source level, you're able to prove indeed that, here you see the equation, half plus a half times, well, it isn't called alpha, but phi here, is equal to phi, and this is what you're going to solve. Yeah? Okay, let me stop. I go back to this perspective in this Nature paper. What is the main motivation of this statement, revolutionary? Because according to the author, probabilistic program obviates the need to manually provide inference methods. And we have seen in my talk, inference in my world is called WP reasoning. It enables rapid prototyping. It's quite easy to write down such a program rather than drawing a huge Bayesian network. And moreover, it clearly separates the model, the program, and the inference procedures, WP reasoning, or model checking if you want, if you prefer model checking. Yeah? This clear separation is there. Okay, so take-home messages. WP reasoning provides exact reasoning of Bayesian networks, but in particular of program code level. Termination has several nuances. We have discussed this, and it's hard. But there are some proof rules that are able to prove, I would say, hard problems. And to my opinion, it's an excellent playground for formal verification, not only deductive, but also other formal verification techniques. We have some extensions to also reason about the runtime of a program. So how long will a probabilistic program run on average? And one recent result we had is about Bayesian networks. So if you now give me some simulation technique and a Bayesian network, by means of WP reasoning, we are able to exactly compute how much time you need to do the simulation. Yeah? Upfront, not by doing the simulation. People that have done some bound-up model checking, so linked to Bayesian networks I mentioned before. Invariant synthesis is a very active field. I only showed you one relatively simple example. Many groups are working on different kind of actually invariant synthesis. And that's it. Thanks.
Okay. Questions? Any? Yep.
So you mentioned invariant synthesis. Do you also see a way of synthesizing variance?
Sorry,
do you also see a way of synthesizing variance for the termination proofs?
No, I don't see this yet. No, this is hard. I mean, it was already very hard to find this proof rule. So, it's very hard to. And for simple examples like the symmetric random walk, I think it's doable, but otherwise it's not easy. Yeah, so definitely this is an interesting thing to do synthesis of those variant functions. Yeah.
Sort of a philosophical question. Why not work denotationally? Why be so tied to working at the program code level with syntactic techniques?
Well, it's in a sense a kind of denotationally, right? You mentioned denotationally, or?
Yes.
What do you mean by denotationally? I mean, I think that WP reasoning is also something which is pretty denotationally.
There was a point in the talk when you showed like the pushdown Markov, I think it was the pushdown Markov chain, and you said, I'm not going to analyze this, I'm going to do this just by syntactic techniques. And
yeah. What I mean by this is I don't want to reason about the operational thing. So I'm not interested in getting the infinite state Markov chain and doing reasoning on this infinite state Markov chain, which you can also do, of course. Yeah? This technique is doing the verification on the code level and not on this push-down Markov chain, or not. Of course, there is a correspondence, so I think that's definitely important to show what results in this world, basically how are they connected to results in this Markov chain world. Yeah? But I was emphasizing the fact that we do reasoning on the program level and not on the Markov chain level.
How do things change in these problems when you go from discrete distributions to continuous distributions?
Semantics-wise, you need to cope with measure theory, and in particular, I mean, this has been done, right? So Katoen people looked at without the observe statement. I must say that. So that's and the observe statement is not easy. I had conversations with Dexter, and Dexter said, "Oh, this is crazy. You should not do those observe statements all around the program." I tend to agree with him, but this is the way people use it, right? So I cannot ignore how people use those things. So we have to deal with this, and it's not clear yet how to do that. Yeah, there is a LIX paper of Hong-Seok Yang, I think it was this year, that goes in that direction, but it's not easy. So this is one of the things. And this reasoning thing, of course, also, I mean, this WP reasoning is strongly focused on the discrete case and not on the continuous case.
I guess in many practical cases, if you want to encode real problems into probabilistic programs, you need such kind of big tables that will have to be converted into these huge ifs.
Yeah.
But then essentially you have these big tables, and wouldn't be interesting, instead of focusing on loops, to do somehow weakest precondition reasoning with data structures? Say I have some database. What would happen if I combine it with some other database efficiently?
Yeah, so let me first focus. The Bayesian network was just an example. I'm not going to write down those if then else statement myself. This, of course, can be automated. Yeah? Input the Bayesian network, you generate this program I showed you. Yeah? So this is easy. And then, of course, that's what of my interest, to apply these kind of techniques to more involved applications. And one of the things we're planning is also to look at probabilistic databases, so databases where you store information with uncertainty. People in databases have their all kind of different semantics, open world, closed world semantics, and so on. And I mean, one of the things I would like to start looking at is indeed how to be able, if it's possible, to apply these kind of things on that world as well. Yeah.
More questions? Somebody? Okay. So I had a question on the, not particularly on the Bayesian networks, but like, so these are loop-free programs basically, right? The Bayesian nets can be encoded.
Not anymore if you do conditioning.
Right, but so many of them kind of, so if it's loop-free, kind of, you don't need the weakest precondition in some sense. You can just do direct inference, right? Yeah. So I guess the weakest precondition though is also useful there if you somehow care about particular invariants that you want to prove, even in the loop-free case, right? Yeah.
But in particular, there also works on recursive Bayesian networks. So Bayesian networks where you have loops,
sure.
And that's also, I mean, like the person I mentioned, Noah Goodman on cognitive science, he uses recursion in Bayesian nets, and there you can also. That's why I also I think it's important to look at things like recursion and also at loops. Yeah. That's also the main incentive of having probabilistic programs. That's why this AI community is looking at those programs, because they want to have loops, they want to have recursion. For them, it's not enough anymore to have those acyclic directed graphs.
Good. Any more questions? No more questions. So let's thank Joost again.